In the previous video on majority baselines, we defined one of the evaluation measures, that's accuracy, as the correct classifications divided by total number of test instances. But this is not the only measure you could have. In general, you need to know of each of the classes. So of the positive class or the yes class, how many you got right and how many you got wrong. Similarly, of the no class, how many you got right and how many you got wrong. So for a binary classification task, you could create a contingency table or a confusion matrix, such as this. If you have two possible labels, so it's a binary classification task, you will have 4 cells, true positive, false negative, and true negative. The true positive is really are the number of instances that were actually yes and you predicted them as yes. So the positive comes from the actual label. The positive comes from the predicted label, and whether it's true or not comes from whether actually it is yes or no. Okay, so the rows here indicate the predicted labels and the columns indicate the actual label, the true label. Okay, so if you create a contingency table like this for a binary class, it's a 2x2 table. For a multi-class classification problem, you may have, let's say, if it's 3 classes, yes, no, maybe, you could have a 3x3 matrix or some other way to kind of create all of these combinations. Once you have written down those numbers, accuracy could then be written, could be actually computed as true positive plus true negative divided by all instances, so total number of instances, right? So in this particular case, so accuracy, for example, does not really tell you what kind of mistake you're making. 1 minus accuracy, which will be error, would just be the false positives and false negatives together. If you are interested in those numbers separately, you have to come up with 2 different measures. So precision is the measure that says of the things that were predicted yes, how many were actually correct, right? So how many were actually yes? So that would be true positives divided by predicted positive. So predicted yes, and predicted yes is basically true positives from plus false positives. So precision is of the things that were predicted yes, how many were correctly predicted. Recall is looking at the column yes. So of the things that are actually yes, how many were predicted yes? So that will be true positive divided by true positive plus false negatives. So this tells you the true positive rate. A more common name for this measure, for recall measure in medical community, is sensitivity, right? So sensitivity is the same as true positive rate, is the same as recall, and that is of the things that are actually yes, how many were predicted yes by the model. Because they are talking about 2 different things, precision is of the things that were predicted yes, how many are correct, and recall is of the things that are actually yes, how many are correct. One measure that kind of combines the 2 is F1. F1, or the F measure, gives equal weight to both of these concepts, and it's the harmonic mean of precision and recall. So in mathematical terms, it's just computed as 2 times precision times recall divided by precision plus recall. Okay, and that's basically the mathematical formulation of harmonic mean of these 2 numbers. That number then would tell you that the higher precision and recall are, the better the value is. F1 would be higher. But then it gives you a measure that is in between the 2, but not really an average of precision and recall. It is a slightly different average that gives them kind of equal weight. And you could change that weight. If you think that precision is more important than recall, you can adjust it. It will not be an F1 measure, but it could be a F.5 or F2 measure, and so on. Okay, that is also possible mathematically. Typically, people just report F1 measures. The other other kind of evaluation metric that is common in health informatics and in medical informatics is specificity. And specificity has to work with the actual no column. Specifically, specificity is true negative divided by false positive plus true negative, which means that of the things that are actually no, how many are truly no, or how many are predicted no, right? Yeah, maybe I should have used a predicted no there. So let me repeat the definition for specificity. Of the things that are actually no, how many are predicted no? So that will be true negative divided by false positive plus true negative. And in computer science literature, it's typically common to say precision and recall and F1 as their combination. In health informatics, clinical informatics, it's typically common to say specificity and sensitivity. They are not the same numbers. Specifically, precision is not the same as specificity, but they are still doing kind of computation of around this confusion matrix, right? Giving you two different numbers. One focusing on false negatives, one focusing on false positives. Okay, so in general, you can actually have many more such numbers. So true positive rate is the same as recall or sensitivity. True negative rate is the same as specificity. That's 1 minus false negative rate. False positive rate is also called fallout or false alarm rate. False negative rate is called miss rate. You have precision has another term called positive predictive value. There's a negative predictive value, false discovery rate, false omission rate, and so on. A good place to actually have all of those definitions, and I typically print this one out and keep it because it kind of summarizes all of these different measures and also tells you what the type 1 error and type 2 error is. This is coming from Wikipedia, the version of this table has changed over a period of time, but I think this one is a more comprehensive version that has all of these names written out. So let's take an example and see how to compute this, or how to kind of build these or build this confusion matrix and get those numbers. I would like you to do this exercise with me. In this exercise, we are kind of we are going to fill this contingency table for TB testing. You are told that there are 600 tuberculosis patients and 400 healthy patients, so 1,000 people in all. And for the tuberculosis test, 80% of the tuberculosis patients were tested positive, the rest were tested negative, and 95% of the healthy patients were tested negative, and the rest were tested positive. So it is a binary classification task, so I would encourage you to take some time and fill out a contingency table and calculate accuracy, precision, and recall for this new TB test. I would encourage you to kind of pause this video now and work it out yourself, and then once you're ready, move on and we can talk about the results that you should have gotten. Okay, let's look at the solution for this exercise on TB testing. You are told that there are 1,000 patients, 600 of them are tuberculosis patients, 400 are healthy patients. So in this contingency table, you have a 2 by 2 table here. There are 1,000 patients in all. The actual yes is 600, actual no is 400. The next line is 80% of those that are tuberculosis patients are tested as positive. The rest are tested negative. So 80% of 600 is 480. So that will be a true positive. And if 480 out of 600 are true positive, the rest are tested negative, the false negative are 120. The next line of information you have is that 95% of healthy patients are tested negative. So that is true negative is 95% of 400, so that should be 380. And the remaining 20 then are false positives. Once you have filled up this table, it becomes very easy to calculate the numbers that you want. So precision is going to be true positive divided by predicted yes, predicted positive. So that's going to be 480 divided by 480 plus 20. So that means 480 divided by 500. So that is 96%. Recall is going to be true positive divided by actual positive. So that is 480 divided by 600. That is 80.80. So 80%. 0.8, and then accuracy is this diagonal, so it's true positive plus true negative divided by all, so that's 480 plus 380, that is 860 divided by 1000, or 86%. So you'll see that precision is 96%, recall is 80%, accuracy is 86%. They are all different numbers, and they are all kind of looking at this table differently, right? So just so that we know and fill up the other numbers, specificity would be true negative divided by actual negative. So that will be 380 divided by 400. So that is 0.95. And sensitivity, which is the same as recall, is 0.8. In fact, you need not have computed these last two. These are the two numbers that are given to you. When they say 80% of tuberculosis patients were tested positive, that is in fact sensitivity. Or 95% of healthy patients are tested negative, that is in fact the definition of specificity. So, so those two numbers are actually given to you. You don't have to use the table in this particular case to get the number, but you see that they are all kind of derivatives of this contingency table. Good. In addition to these numbers, you also would see something called a ROC curve, that is a receiver operating characteristics curve. This is a plot, a graph of true positive rate or sensitivity on the y-axis and false positive rate or 1 minus specificity on the x-axis. So this is an example of an ROC curve. It's usually common to have multiple ROC curves on the same plot if you're kind of comparing two classifiers, in this case C1 and C2, on the same data set, right? What this is showing you is that at the point here 0, 0, the false positive rate is 0, which means specificity is 100% specificity, and 0% sensitivity. What does that point mean? I am not making any mistakes. So the false positive is 0, but I'm also not finding anything, right? So the true positive is also 0. But it is common to see that as you identify more instances, so as true positive rate increases, the false positive rate also increases. And that is this trade-off between specificity and sensitivity, right? The dotted and dash and dot line right in the middle there, the 45-degree line, is really where for every new instance you get right, so every new addition to true positive rate, you find one that is wrong. So you're increasing false positive rate also. So obviously that means that you're not really doing much. For every correct thing you're identifying one that is incorrect, right? So you want your graphs, your plots to be above that line. In this case, both C1 and C2 are above that line. Is there a difference between the two? I mean, the C1 is identifies many more things correctly without losing too many in the false positive. So the false positive is lower, but the true positive suddenly increases. But then later on, it starts making more mistakes. Whereas C2 kind of makes more mistakes early on, compared to C1, but then eventually makes less mistakes as more and more instances are identified. Which one of these is better? One way to kind of compute that is by using area under the ROC curve. So area under this curve would tell you how many of the instances are actually getting right? So this is called AUROC number, or sometimes called AUC number, area under the curve. And that would tell you of the two, the one that has higher area under the curve would be a better model. But you could see in this case, even though they may have very similar AUC curve, suppose your condition was that you don't really want to make too many mistakes and you want to get to 80% quickly, right? So you're okay with only getting 80% instances right. So the true positive rate is 80.8. Without making too many mistakes, then you will see that in that case C1 is better, because C1 gets to 80% really with about zero point 0.2 false positive rate, whereas C2 gets to that level only around 0.4 false positive rate, right? So you need to that C2 is making 40% mistakes to get to a place where it's 80% right, whereas C1 only makes 20% error. So that would be one way of kind of choosing between these models, but it's typically common to see across the entire spectrum, across the entire false positive rate, the one that gives you higher AUROC would be better. Okay, to summarize, the key takeaway from these evaluation measures is that you could have multiple measures of evaluation, and domains have their own preferred measures. Accuracy by itself is not a good measure, because especially when the classes are imbalanced, that means one class is larger than the other, it doesn't tell you what kind of mistakes it is doing. The precision, recall, and F1 measure, and specificity and sensitivity are typically better measures, but they come in pairs. So precision, recall come together, or specificity and sensitivity come together, right? They can be calculated using contingency table. Composite measures such as F1 or AUC or AUROC are kind of combine these two. You note that AUROC is basically a combination of sensitivity and 1 minus specificity.